So thanks so much, Heidi. As Heidi mentioned, I've been a engineer here at Red Hat for quite a while doing security stuff, and I'm really thrilled to introduce our next speaker, Richard Habeeb. Why don't you wave to us, Richard?
Yep.
And Richard is a PhD student at Yale, and he's doing really fascinating research on the provability of enclaves. So I will let Richard take from here. Give you as much time as you can, Richard. Thanks so much for coming today.
Yeah, hi. So as Nathan said, I'm a PhD student at Yale, and been working on doing some research on enclaves. A bit about our group: we are sort of a mix of some systems researchers and also programming languages and program verification researchers. And we're really interested in building safe and secure systems with sort of formal guarantees about them. Okay, so a little bit of the setting of the problem that we've been looking at. Say you have some high assurance application or privacy sensitive application, and you need to outsource this computation onto the cloud or possibly even an edge device. In order to do this, you oftentimes have to trust sort of many layers of software, including the operating system, hypervisor, etc. And this can mean that you're relying on potentially tens of millions of lines of code. So you have to rely on many layers of software, and there's been sort of historically many vulnerabilities in this sort of large trusted computing base. One emerging approach of dealing with this issue is the use of out-of-box hardware features provided by Intel, AMD, and other chip vendors in order to create enclaves. An enclave is sort of an isolated region where you can run code in a secure way. It's originally designed for DRM purposes, and the idea behind it is you use cryptographic signatures in order to attest sort of the authenticity of a loaded piece of software. But what's cool is we can sort of invert the relationship here and do sort of way more than the original design intended and get better security guarantees. So one thing that we sort of envision as a future of what you could build with enclaves is you could have sort of a set of isolated enclaves or these sort of secure processes running across multiple cloud nodes, some of which may interact with a GPU or rely on multiple cores to compute. And the overall computation itself is sort of as if it was running within a single process or within a single sort of security domain. And you can abstract away a lot of the details of the sort of the different systems. And furthermore, you could potentially also reason about the security and correctness of this distributed system as a whole and the computation that it's trying to do. And this is sort of an aim of what we could accomplish with this kind of work. An example of this might be, suppose you have a mobile device, and on your mobile device you have a secure messaging app, for example, Signal. And Signal could run within an enclave on your phone, so it's not modified or so the private messages are not leaked. But you could also have some outsourced computation, say, for example, a secure contact discovery service that also runs in the cloud. And this way, you could come up with sort of the cloud would operate as an extension of the phone's computation, and the phone could sort of be sort of sure that it's not leaking any private data to the cloud OS or potentially even the cloud vendor themselves. And we're also interested in taking this and potentially even proving some isolation theorems about the entire system. Another example of this might be autonomous vehicles. This is obviously really an exciting area. There's a lot of new developments, and one of the ways that autonomous vehicles may be deployed, and one of the first ways we imagine will be through ride-sharing companies like Waymo, Zoox, and Cruise. And these vehicles, they occasionally will get stuck and need some remote support from an operator. And in these cases, your vehicle needs to be internet connected, and the vehicle has a sort of a stake in knowing that it's taking commands from an authentic and sort of a real operator and not an adversary. And the companies themselves operating these fleets of vehicles have a stake in knowing that the software running on vehicle hasn't been modified by some sort of adversary in the field. And this is a situation where enclaves could provide that sort of assurance through attestation. So one of the sort of main questions driving our work is, can we support this kind of real world, high performance, concurrent and secure outsourced computation while also getting some of the formal guarantees that you want when it comes to security? So let's first talk about some of the background of our work and what's been done so far. So first of all, one of the really popular methods for creating enclaves today is using Intel SGX. And Intel SGX is an extension to the Intel architecture with some special instructions that allow you to create an enclave for a user space application. And what happens in a sense is an application is sort of bisected into an enclave part and a non-enclave part. And you as a programmer have to decide which parts of your code will live within the enclave and which parts don't. And you use their SDK in order to sort of switch between these two parts. And the hardware provides some instructions which are implemented in microcode in order to sort of create this environment. So there's been a lot of work in this area. One of the big problems with this is that enclaves, if you write an enclave for an application for this system, it's not very portable. It also, a lot of work has shown that there's a lot of potential side channels that can crop up with this. An enclave has to be sort of a user space application, which can limit the potential for protecting an operating system enclave against the hypervisor. And there's some performance implications, particularly around the system call instruction, which is disabled while you're within the enclave. Another sort of major style of enclaves is sort of similar to the ARM trust zone system. And other technology like AMD SEV sort of have a similar kind of pattern in a general sense. But the idea here is that the system is sort of bisected into various security domains. In ARM, they would call it normal and secure worlds. And in these security, in these security domains, you would sort of have potentially you would divide untrusted and trusted software in such a way that your enclaves would run in a secure world, and they would not need to trust sort of a full operating system like Linux, but maybe you would have a minimal secure operating system that they would have to trust. And that operating system would have some dedicated memory, for example, that it would use. And then switching between these worlds is done by a lower level piece of software that's usually implemented in firmware. One of the downsides of this is you still have some of the issues that you have before, where you have a large trusted computing base, and because you still have to trust this sort of operating system in order to run an enclave on top of it. So some of the challenges, to sort of wrap up quickly here with this part of the presentation, is that existing solutions are often not portable to the different kinds of architecture. As you can see, the ARM and Intel are very different in terms of how they define and set up what an enclave is. And there's not really great support for multi-core or multi-node notions of what an enclave is. And thirdly, you have to trust a lot of software, and there's not, and hardware, and there's not a lot of strong security guarantees that you can derive from the system, from using these systems. We also have several constraints in terms of performance and security. We're trying to minimize context switches, the amount of time it takes to attest a process, and minimizing the amount of time it takes to do system calls and I/O, as well as dealing with side channels and potentially supporting accelerator use in a secure way. So our design for potential solution for this starts with sort of looking at what an enclave is in sort of the smallest, in the most sort of general way. And what we wanted to do is define sort of what is an enclave in a logical sense. Essentially you have some code and data, and this code and data has an underlay or functions that it uses from either the operating system or other libraries. And it has an overlay or an interface that it provides to the outside world. And what we argue is that for an enclave, if you can show that there is non-interference with the environment, essentially if this region of code and data is isolated from both reading and writing and other sorts of side channels, then you have isolation. And if you also have that in addition to attestation, these are sort of the essential components of what makes an enclave sort of secure and separate from a process. And of course, the environment still can affect input and read output to the enclave. And we've defined this non-interference in a very general way as sort of not necessarily including virtual memory abstractions or MMU protections. And I'll talk about sort of why that is later. All right. And starting from that single enclave, you could potentially also think of building sort of a larger chain of trust from this single component, right? So if you have an attested enclave, that enclave could start another enclave and attest that sort of component of code. And the result of this is you could build a chain of trust of a more complex system within an untrusted environment, assuming you have a single sort of foothold. You can also think of these as sort of potentially a sort of fine-grained unit of concurrency, and we'll talk about that later as well. So putting these things together, what we could build with this system is some sort of generic enclave platform that abstracts away the lower level details of what the architecture or platform provides, but provides sort of a clean set of a clean interface for starting enclaves and sort of in interfacing with them. In this generic enclave platform would allow a remote client to attest, and it would also allow sort of a chain of trust to be built on top of it. So where we're going with this is we want to use the Certicos framework, which is an operating system in Hypervisor that our group has developed to build and verify a concurrent multi-architecture and compositional enclave platform. So as I just said, Certicos is this kernel and hypervisor. It's about 11,000 lines of code. And what's interesting about it is that it's developed using a layer-based technique. So using sort of principled software design techniques of modularizing each part of the code, we can create layers of abstraction that build sort of a very complex operating system using simple components. And these simple components themselves can be very easily verified, or more easily verified than trying to do the kernel itself as a monolith. And what's interesting about this as well is you can also use this sort of modular technique in order to create sort of a multi-core kernel, and that's sort of a lot of the work within our group has gone into making Certicos verified and have support for a multi-core system. So in order to sort of reason about each of the layers within Certicos, we've defined sort of a calculus, which is a sort of certified abstraction layers. Each layer has an overlay and an underlay and an implementation. And what this calculus does is allow you to sort of combine layers and reason about them in various ways. And so here's some examples of that combination. You could have horizontal or vertical. I think vertical is fairly easy to understand. If you have, for example, some software component which uses a library, so it makes some function calls into a library, you could sort of wrap those to the software component and the library into a single layer themselves, which expose some outer API to the upper layers. And so there's also parallel composition, which is dealing with two layers that may need to run on different cores or in concurrency with each other. And all of this is sort of allows you to take C code and compile it down to verified x86 ELF files using a certified compiler compcert-elf. So what we could do with Certicos, and there's a few different architectures that we can support with this kind of system. And the first and sort of obvious one is that you could have Certicos running as a hypervisor. And how this might work is at boot time, you have a trusted platform module, or TPM, which attests to the authenticity of the BIOS and the hypervisor. And from there, Certicos itself can run virtual machines and provide those virtual machines with an interface to launch user space or kernel level enclaves. And you can use potentially use various technologies like AMD SEV in order to get memory encryption, so you can protect against some physical attacks in this case. One of the downsides, of course, of this approach is Certicos doesn't have all of the rich features that you might get from a fully fledged hypervisor like Zen or KVM. These will have more device emulation, for example, more devices that they can emulate. Another sort of more practical way of deploying the system, which we also think is good in the sense that you could get some security benefits from it, is you could have, in a context on the cloud where you can't sort of modify the low-level hypervisor that's running, you could assume that, okay, we can't modify it, so we have to trust it, but we can still get isolation and we can still prove isolation between a virtual machine running on top of Certicos. I didn't sort of write it in here, but that virtual machine would be nested, so you'd use nested virtualization, and that untrusted operating system could launch enclaves, and using Certicos, you can still get formal guarantees that any enclaves that virtual machine launches will be isolated from the untrusted OS. There's a few limitations with this approach. Nested virtualization can be slow, and as I mentioned before, you have to still include a large hypervisor in the chain of trust, which can be non-ideal, but there are some benefits to this. Another architecture, and one that we're really excited about supporting, is this split hypervisor approach. And in this case, the idea here is that you divide the functionality of a rich hypervisor like KVM into a high visor and low visor. And the low visor itself operates in, for example, VMX root, so at the lowest as the true hypervisor, and it will do all of the necessary functions that involve reading or writing memory of guest OSs. But all of the features that don't need to be within the low visor are exported into the KVM, which runs itself as a sort of a virtual machine or as a guest OS on top of the low visor. And so what you would get in this case is Certicos would provide 3 different APIs. One would be an API for the high visor in order to launch and switch into and manage the virtual machines. The other API would be for the virtual machines to sort of communicate with the high visor. And the third API would be to launch and manage enclaves. And I guess you could also potentially have a fourth if you wanted to support system calls for those enclaves as well. So in this case, you would get, Certicos would allow you to prove isolation between a high visor, an untrusted operating system, and any of the enclaves running on top of it. And you would still use the TPM, of course, to bootstrap that chain of trust. And what's great about this design, which is originally coming out of Columbia, is that you can get better performance than the nested virtualization case. Okay, so I mentioned before sort of Certicos being made out of layers and the idea that you can merge these layers. The idea behind our design is that you can actually potentially do the exact same thing for enclaves, which are sort of very, very similar to layers or components. So you could, as a performance optimization, if you can show that 2 enclaves can sort of live within the same address space and won't interfere with each other, and you can show this using formal verification, then you could merge them together vertically, like I've shown here. And you can reduce the number of signatures that you need to check in terms of doing the attestation. And you can also reduce, reduce the number of context switches that you need to do in and out of enclaves. So it could be a really good performance optimization. And you can use this idea to sort of build Certicos up as instead of layers, you can think of Certicos as an enclave that's built up of other smaller enclaves itself. And so in this diagram, we basically have hardware components on the left and sort of the system that we want to build on the right. And each yellow box would be sort of an element that we're trusting, or an element that, basically an element that we're trusting. And you can show that an enclave here on the right-hand side you can draw this chain of trust backwards through the various components of Certicos. So for example, going back, and if you want to like have some IO, you can show that the enclave relies on the parallel disk implementation, or which relies on the underlying sort of disk driver enclave. And ultimately, you will end up relying on some hardware, right? So at the lowest point, you're like, okay, this disk driver has to trust that the hardware sort of does what it says it does. And from the verification world, we just model what that hardware does in a detailed sense. So what we've done so far, as far as working on this, for the past few years, we've been working on a multi-architecture version of Certicos. And this multi-architecture version supports, x86, ARM, and RISC-V. What's really exciting about it is it has a very, it can support all of these different architectures and platforms as well, by building up sort of clean layers of abstraction. Say, for example, you need to have a clock and a timer in order to sort of do the scheduling that you need to do for an operating system. Well, each platform may have its own version of the timer, and so we implement the clock and timer as these sort of generic interfaces, which are implemented at sort of the lower level by these devices. And you can compose all of these together in the verification sense to show that the composition of each of these different components or layers builds up sort of a more complex system like a scheduler. So on the left here, we basically have all of the different architectures, x86, ARM, RISC, etc. And in the white box, you would see like basically all of the different sort of architecture specific implementations. And in these sort of like transparent boxes, or the blue boxes here, you have basically the layer of abstraction that it relates to. And similar, you have the different layers of abstraction for platforms over here in the device tree region. And then up here in the core part of the tree, basically you have all of the highest level functionality of the operating system that doesn't depend at all on any architecture or depend on the device tree details. So sort of a very clean way of building this OS that provides a nice interface. And we've been working on, in particular, implementing some of the features that we'll need to build sort of Certicos as this Enclave platform. And that would be one of the particular layers is this attestation part, right? So the operating system itself will have to be able to attest any enclaves that it starts. And then sort of another direction that we've been going with this is on the ARM side specifically, we've been taking multi-arch Certicos and running it within the trust zone of an ARM platform. And doing that in addition to writing our own firmware or runtime services. And the benefit of this is we can have this verified software chain that goes all the way from the lowest level of firmware up to the secure OS. And we can show that any enclaves that you're starting on top of Certicos in the trust zone, we can sort of formally verify that they are isolated from the software running in the normal world.
For those people who are coming into the room, feel free to post questions in the chat, and we can direct those to Richard when he's ready. So yeah, Richard, please continue.
Yeah, I was just about done. I basically just had the conclusions slide left. So yeah, I think sort of what we see sort of the main contributions of this work is building this layer of abstraction that sort of covers over all of the architecture and platform details, allowing enclaves to be portable to different architectures, using the relevant and useful technologies that are provided by chip vendors in order to build enclaves, and then using program verification and compositional design to verify the security guarantees of this system. But yes, so that's at a high level oops, excuse me. This work. I'm definitely happy to take any questions or.
Well, while we're waiting for people to type up their questions, I'll go ahead and start. So my first question here is about side channels. I know that there has been, over the last few years, quite a bit of concern and research about side channel attacks. And as the slew of SGX vulnerabilities has taught us that enclaves are not immune to these kinds of attacks, have you done any research on ways that you could use this kind of framework to proactively defend against side channel attacks?
Yeah. So one of the benefits of doing this kind of formal verification work is you have to build a detailed model of what the hardware does. And if you actually have a very detailed model of how the microarchitecture works, you have the benefit of reasoning about it in ways that can eliminate these side channels, right? You can, you have a model, for example, of how the cache works, then you can verify that you've cleared the cache appropriately when you do these kind of switches. That, of course, requires that you have a really rich machine model, but that's one of the benefits of using program verification. But yeah.
Thank you, Richard. Does anybody else have any questions at this point?
I had a question. So I'm not by any means a security expert, but certainly listening to the compacted explanation of the project, it seems extremely complex. And I know you were talking about making the clean layers for developers to be able to interface without knowing or maybe having to pay too much attention to being in a certified system. Can you talk more about how you envision that can actually be simple or usable? Like, what do you have to do for the programmer's convenience beyond the certification part?
Yeah, one of the projects that our group has been working on, I can speak to it a little bit, is we actually have a programming language called the Deep C. And the idea here is that it can allow a programmer to write, not have to think about writing a different sort of C implementation and all of this specification of what their software is supposed to do, but it allows sort of a programmer to have a nice clean programming language for writing these kinds of compositional systems. And what it does is it also does a lot of the tedious reasoning, or it automates a lot of the tedious reasoning that you have to do when it comes to doing program verification. So it can make the job a lot easier. The other thing I think that's important with this work is, we also think it's really important to support sort of legacy software. And so a lot of our work is, we want to be able to allow components that sort of have been written by sort of without thinking about the overall system in mind, be able to integrate with this compositional design in a secure way, so that you still get some security guarantees. I didn't sort of go into detail about that, but yeah, that's sort of one of the aims of this work.
Thanks, Rich. We have a question from Ben Fisher. How do you see enclaves being adopted by the market in the future?
Yeah, that's a good question. I think they're really, I gave the two examples at the beginning of the talk, but I think you can make a really good privacy case for a lot of different applications. For banks or hospitals, they have a lot of sensitive information, and they also have requirements from either governments or other standards organizations of like how this data needs to be handled. And so enclaves in general can help with that. And, you know, if you also have, you know, some of with the work that we're doing, you could use program verification to have sort of more stronger guarantees about the privacy of that data that you're trying to protect, instead of just needing to go off the claims of Intel or other chip vendors, for example.
I think I can add a little bit. So we are seeing more and more security critical applications. We anticipate, I mean, the kind of enclave we provide is something that we, you know, what we call, we have a certified trust. You know, you can't just tell people that, oh, here's something running inside the enclave, and you don't have an assurance case to support your claim. So in the, you know, in many community or in many application domain, you know, one of them probably is a smart contract, right, running on blockchain, and there's a urgent need for you know, developers to provide assurance case why a particular smart contract is free of bug, because otherwise any bug could lead to huge, you know, financial loss. And so that kind of we anticipate there will be lots of such applications in the future, and where the market and the, you know, the particular application domain would demand some third-party checkable evidence, which our, you know, enclave, the certified enclave, will try to support. So we are hopeful that you know, there will be more and more needs and more applications, domains that really require this kind of third-party verifiable, you know, enclave domains. And I want to just mention that I mean, the fact that most hardware vendors are putting out different hardware enclaves, and also multiple companies are interested in building software, is kind of evidence that there's a lot of also.
Thank you. We have another question from Heidi. Are there different security levels for enclaves built into Certicos, or are they all the same above a threshold that makes them certified?
Yeah. Do you want to answer this?
Sure, I can answer this. So the notion of a security level, I mean, normally we use the number 1, 2, 3, 4, and I will anticipate that, you know, had you asked the question, you know, how would be the end user experience will be like using this kind of enclave API? I mean, we anticipate there will be many different kind of clients or users who want to use this kind of enclave infrastructure, because you know, at the user level, we assume the user just need the peace of mind that they are running their code inside the enclave. And ideally, we want to provide APIs that resembles the legacy API, so people can port their applications quickly into these enclave. And in that sense, some number, the notion of security level might be sufficient. Basically, this security level will tell people, you know, what kind of isolation support you can provide, and what kind of basic assurance properties we can provide. But at the system level, which Richard actually showed in some of the later slides, we anticipate a kernel developer or even the cloud vendors would be interested in put together system level enclave where you would really care about you know, detailed API, system enclave API, because now it's about a particular device, like on a self-driving car. You'll be wondering, you know, how much trust you can put into camera, machine learning module, and you know, all these other devices on a car or on a cloud setting. And so those levels are not as simple as a number, but rather it's a assurance case saying, you know, if you have a multiple hardware device that can provide some fault tolerance, and if there's some logging support that at a runtime, even if we have some code that's not verified, but we are going to log all the events, then the kind of assurance case we can provide would say, oh, even if a self-driving car could still get into an accident, once the accident, after the accident, we can at least look at the log to figure out which component is to blame. So in that sense, the security level will be much more concrete, related to specific functional specification and API specifications.
Thank you very much. We have another question from Ben Fisher. Where is the future of your work headed?
Yeah. So I think, we're really interested in building, lots of different kinds of systems. I think one of the big projects that we've been working on right now is actually sort of a prototype for a self-driving car. And that's sort of the idea there is we actually want to build, using MultiArch Certicos, a system where you have, maybe a collision avoidance system or some other critical software running in Enclaves, and actually really show that this is, that those are isolated from the Linux operating system that runs sort of the main AI of that vehicle, or maybe runs some of the other external interfaces. I think that's one sort of direction that we want to take this. There's also, I think we're really interested in building a cloud-supported kernel as well. So like something that can run on a cloud device as a hypervisor or otherwise that really can support enclaves in a high performance way. But yeah, I think, there's a lot of different, the software we're working on is pretty generic. And so there's a lot of different applications. But yeah.
I guess I want to just add, in the context of a Red Hat research community, I personally, I am, extremely interested in this split visor scenario 3 that's described by Richard in his talk, because I think the community is really demanding a secure platform that are 100% or at least 99% compatible with the legacy software and the legacy toolkit. There's lots of today's system, whether cyber physical system, whether cloud system, that are built on top of Linux platforms. And if something that can be done to provide a scalable enclave in that ecosystem and offer the functionality of certifiable trust while maintaining, almost 100% compatibility with the existing toolchain, that would create a really interesting evolution path that people will start to move some of the functionality into Enclave, and that would slowly create the kind of ecosystem that you can have certified components even for cloud level applications. And I think that'll be even important for other type of security mechanism like multi-party computations, and because you have to have something to bootstrap trust. And the bootstrap trust is not just attestation by saying this is the code done by a particular vendor, but rather it's a certified chain of trust that can put together formal verification proofs and the actual property you can certify, and plus the mix of these other, attestation and authentication mechanisms. So that's the part I see a bright future of, the kind of work we are pursuing right now.
Yeah.
Thank you very much. I have a question about secure devices. So one of the challenging things that we've seen in our early experimentation is question of like a trusted view of time, for example. Imagine in the cloud scenario where you have the host claiming that you've spent, so many seconds or minutes or hours of billing, and you, however, are not sure that you can trust the cloud provider, because this is precisely the reason we're using these enclaves is so you don't have to trust the cloud provider. So how do we have an independent source of time on that system, for example, and other secure devices that can provide what we might call an unbiased view of the world?
Yeah. I think one of the directions that we've wanted to take the development of MultiArch Certicos is the ability to provide enclaves with sort of an independent access channel or API to various devices in a way that an operating system or hypervisor sort of doesn't have access to that device. And so one of the work of this sort of that we want to have the generic enclave platform do is actually sort of do some of the low-level resource management in terms of saying, okay, you could say, okay, this clock should be dedicated to this enclave or this set of enclaves, or could provide a generic time API, for example, to set up enclaves. Yeah.
Thanks. One of the other things you mentioned, which is sort of related to this, is that you had intended to support things like accelerators. And I know that the situation today is sort of precarious regarding enclaves because, if you have something like a crypto offload engine, really that's outside of the trust domain of the enclave. So you would have to then cross a trust boundary in order to be able to use that those accelerators. Have you done any consideration or work on how we might be able to extend the trust boundary from the enclave onto specific hardware subcomponents like crypto offload engines, FPGAs, GPUs, etc.?
Yeah. So this is an area, I think, for us that is in our future work. There's another group at Yale that's very interested in sort of doing research on these hardware accelerators, and they already are doing research on these hardware accelerators. And so we've started some collaboration there. I think that world is very, it's kind of the Wild West. There's like not any sort of standards or there's not always a go-to way of doing things yet. And so, but I think one of the directions that we're aiming towards in general is being able to provide, because the operating system provides this natural layer of abstraction over devices, there's a potential that that we could use that, leverage that abstraction in order to protect the data in transit in between the core that's running and the accelerator itself. That, of course, requires that the accelerator have potentially, some ability to interface with us. But yeah, that's kind of the long-term potential vision that we have in that area.
Thank you. The last question I had was based upon the questability or the question of composability and attestation. These two principles do seem like they are in somewhat of a tension. We obviously like composability as a disciplined software development methodology, but on the other hand, the more composable our system is, the more complex attestation ends up being. And this is particularly the case when you only get when you're using a technology that would only give you, for example, one attestation measurement, which would summarize all of the composable pieces. So my question is, have you given any thought to how you might be able to avoid this tension or make thoughtful trade-offs between the tension of composability and attestation?
Yeah. I think a lot of our work sort of was, as far as composability, was thinking about the static case. So all of the software components being known ahead of time and their organization as well being known ahead of time. But I think there's actually a potential, and in the static case, I think it's fairly easy to sort of think about how to do attestation. But actually using our model, there is, I think, a potential to support sort of dynamic sort of enclave libraries where you have an enclave component that can act as a library that's been attested, where you also have, and you have another user component that's sort of interfacing with that library. You can still, if they're sort of being attested by the system, you can still get sort of a chain of trust between these two. And I think there's potential work to be able to dynamically link these together and still get the attestation at runtime. But there's sort of the way the memory is laid out and all those details are really important. So it's something that I think would be really cool future work. Would be like doing some development in that area.
Thank you. We have another question from Ben. Do you see use cases for an enclave inside of an enclave?
I can take that one. So the very nice theory we had about the logic enclave and how they compose to build a bigger logic enclave means that enclave all the way down. Yeah, it precisely means that we can actually have this notion of enclave inside an enclave, in the sense that you might have different degree, different security level, different assurance guarantees. The outer enclave could provide some basic properties of isolation from the rest of the environment. But once you are inside this outer enclave, you might need even more credentials or more authorization to access some inner enclave. So what we are modeling about the enclave is very much reflecting, what the concrete things you see in the real world, right? In our real society, we already know there's an enclave inside an enclave. We have a different notion of an informal enclave. It's just not something in the digital world, but in the computer, inside the virtual world, inside the software and the hardware abstraction, if you look at the hardware device tree and the MultiArchitecture Certicos diagram, you would already see that a large-scale system are built of these, modules or enclave of many sub-enclave. So we anticipate that the theories, the tools that we develop will be useful for capturing these different application scenarios.
That's great. Thank you.
Yeah, maybe I just want to add a little bit more about the question that Nathaniel, you asked Richard a little while before regarding security of device. I think one of the major challenge when we put together heterogeneous computing platform is because, precisely this, this challenge of heterogeneity, because we have an accelerator, we have a GPU, and it's wide open what are the proper programming model and how these different accelerator, GPU, and hardware device are going to communicate with software running on the, running on main CPU. And there's all kinds of programming model, being developed, and some follow shared memory programming model, and some follow message passing. Some require asynchronous, cause for efficiency. And so those are the places where these, careful research or investigation about abstraction layer, API among these different devices, which in our work is characterized as this hierarchy of abstraction layer of device trees. So wearing my peer hat, one of the work that we are trying to do is to come up with the common API people would benefit from, the actual kind of code you see in this kind of very versatile heterogeneous setting, and hopefully we will have a good recipe for future challenge. And that's where we are heading to, and hopefully we will have a more principled OS kernel or Enclave kernel that helps to divide these system into very clean components. And Enclave is just a kind of a very incremental, conservative way of evolve the existing platform towards the more secure world.
So Heidi, thank you. Heidi asks, are you actively looking at side channel attacks on enclaves? We work very closely with experts in side channel attacks at the OS level in and out of Red Hat, who we might want to connect with you if so.
I do work with my architecture colleague at Yale. We are interested in addressing some of the well-known hardware side channel attacks, but it's mostly staying at the level of like what Richard said, like how do we verify virtual memory management even in the presence of speculative executions and so I think it will be relevant to other groups' work. I'll be happy, of course, to talk to experts on side channel. I know there's many different kinds of side channel attacks, but as Richard mentioned, the very nature of our work is to formalize these different hardware interface and to precisely specify what hardware feature we were actually using. And so by doing that, we have a better understanding exactly, if we want to prove oscillation, what hardware side channel will be relevant in our scenario, and what kind of things we can actually deal with more satisfactorily. I think you muted yourself.
Yeah, I did myself. Thank you very much for that. Do we have any other questions? Looks like there's not any other questions. Thank you, Richard, for your presentation, and thanks to the whole team at Yale for doing really interesting research. And we really look forward to follow-ups on this.
Thank you for being the host.
Yeah, thank you.
Yeah, thank you for coming.
Yeah, thank you.
Bye-bye.
Bye.